Welcome to another problem session. So today we have another interesting problem. So the problem is coming from, I think the first time I saw this was in Klepner and Kolenko, and then I've saw it in other places also, and I've modified this problem to many times to add some color to it. But we're gonna just do the Klepner problem, K and K. I mentioned that this Klepner Kolenko book is very good for if you trying to really master the subject at this introductory level. Okay, all right. So here is the problem statement. So we have a chain. Some of it's already fallen on the scale. So there is a reading. So chain, let's see, it says at t equal to 0. If you draw out the chain at t equal to 0, the scale is the same place. So this is at t equal to 0. The chain is like that at t equal to 0, and this some time t, some is fallen, and this thing is falling, and this chain is going to be fall at the same rate as these guys. The entire chain is straight while it's falling. It's not crumpling around. Okay. And at this time, when you let go, v is 0, but acceleration is g. So the very next moment after t equal to 0, so this is t equal to 0 situation, is going to fall. Okay. Now, so question is like after from here to here is length is x, then what will be the reading here? Okay. And the very interesting thing is you find that, okay, you find the formula, very, okay, colorful formula, okay. But at some time, let's use a different ink. T equals to sometime t, all the chain has fallen, okay. And the last bit fell, okay. And then we have a situation, t equals to t plus just a tiny, let's call it dt. Of course, the chain is all here. This reading is different than that reading, okay. Excuse me. T minus, let's call it t minus. T minus is this, t minus dt. This situation is different in that situation, because this very last bit is still falling, okay. So it's still falling some b. All right. So we need to figure out over here. Are you clear with the setup? Okay. So a couple of things we're going to do is, what are we trying to find? Okay, the reading in the scale, what is that? When you have a reading in the scale, it's reading a force, right? A force that's applied on this. So this reads a force on the pan, force on pan. So let's isolate so we have a pan. So what are the forces in the pan? And so, well, of course, you have supposedly you have teared it, so the pan's weight is already zeroed out. So pan, other than, we want a force other than its own weight. So that's one force. We can ignore that force. So the only force is going to come from the chain. So you'll have some amount of chain. If the chain was L, then the one that's sitting here will be L minus X, right? I'm sorry, this is fallen X. So this is L minus X. And the one that's falling down all the way here, amount that's fallen down is X also. Is this is the amount of chain that is going to be over here. Okay. So this is the X. And it's saying the mass of that, and this at rest. This is at rest. We're going to say when it's false, immediately comes to at rest. We are going to say that, okay? It's not bouncing around or something. So at rest, an amount is X. So mass in the X is a mass of length L. So you have a mass over L times X. So that's the amount of mass there, okay? And then these links are going to hit it. And so they're going to bring the momentum, and we'll say momentum is going to be come to 0 after it hits it. Okay, so they're going to transfer the momentum to the pan. So the question is, what is the dp dt? What's the rate at your moment transfer? So remember the so the force can be from just a gravitational force of the weight and the rate at which momentum is transferred. So this is from this is like a collision problem, right? This is like a collision problem. So there are two parts to it. This part is going to just do mg on it, so mx g on it, and this would do a force, let's call it impulse force impulse, and fj is just be equal to the rate at which momentum is transferred. Well, what is the rate at which momentum transfer? So let's go back here. So this links down here, the v is v, and so what is that v? Is same thing as this link has fallen the same distance. This link overhead that is going to hit has also fallen. It used to be here, so it has fallen distance x, just as this original link had fallen distance x. So all of these are going the same v. So basically what we have is the thing that's falling used to be over here, and it has fallen distance x before it's going to hit it. Well, and it's going to be free fall. So if you drop a link or mass and a distance x vertically, then this v is supposed to be square root of 2gx. It's going to work out like that. If this was v equal to 0 here, and by the time it gets over there, it's going to be this v. So we know that much, right? So this is going to be at the top is delta p, and below is delta t. So this is we're gonna think in infinitesimal time. So it's going with v that much, right? But so this is going to be what's the mass of this link? How much is falling, in time delta t? So mass falling at rate at speed v in time delta t. how do you figure that out? Okay, you can actually, several ways you can figure it out, right? You can say, well, uh, now I'm going to just look at a vertical thing as if it's continuous, so I can, uh, so if everything is going to V, everything is going with a V, we just make it everything going with a V. And so this distance would have gone was V times delta t. And these dt's are, delta is infinitesimal. So if you don't like delta t, physics people like to keep it separate later on, think in terms of limits. Because dt and delta t is, you can mix them, it's not a big problem. Okay, so v delta t, so this is the distance has fallen, so how much mass it corresponds to, this is going to be just like over there, it's going to be m over l v delta t. So this is going to be delta m. So that much mass is will carry a momentum this. So delta m times v in time delta t. So that much momentum is coming, right? That much momentum coming. So so we can write down amount of momentum is delta m times v, and immediately comes to rest. You can if you do this as, if you do that as an x-axis or like that, then this is the final and this is the initial, so you're going to be pointed downward, right? So this is going to be came with this, and if you want to be more like think about direction of the force, this is the x, so this will be the momentum that will have changed for the link. This is for the link. So the link come in and got addressed. So let's and this happened in delta t. So you can write down minus delta m is going to be m over l v delta t, and then gonna be v. So actually it's about minus m over l v squared delta t. So this force is asking us to get the rate at which momentum transfer. So we can just ignore the minus sign for now, because we already took into direction will be there will be mg this way, that's going to be negative, and there's going to be force from this change of momentum on the link that will also be negative, and there's going to add up. And what this showing is that force that this has to apply to balance that other force, right? So we can just ignore negative signs and work with just absolute values, all right? So the Fj will just be equal to this whole thing, m over L v squared delta t over delta t. So this is the rate at which momentum time, and delta t got just cancelled out. So that's why I didn't really do a dt, because sometimes we feel a little bit insecure about cancelling dt's. But you can cancel them, because you can always go to an argument of in small but finite to infinitesimal, meaning take limit, so that's the argument. So this is going to be m over l v squared, and we already know what the v looks like. We know the v looks like square root 2 gx, so this can write out m over l times 2 gx. Okay, so now to recap, we had two forces, one force this, and both of that we know. So the weight of the reading, okay, reading will be this force, reading in the scale will be the force will be mxg plus fj, and then mx was m over lx, m over lx times g plus m over l times 2xg, which is 3 m over l gx. All right, this is the answer. So let's try to interpret this answer a little bit. When nothing had fallen, then the reading will be 0. So reading is f is 0 when nothing fallen, okay? What is nothing fallen means x equal to 0. So this corresponds to x equal to 0, nothing fallen. When the entire chain has fallen, so this is t equal to 0, the t equals to t minus dt, just like infinitesimal time just before it's still falling, so that fj is not 0, then f is 3, then x will be is all l minus little dx hasn't fallen yet. So it's going to be 3 m over l g l minus, let's call it dl. Just a little bit of one chain or fractional chain still hasn't really come to rest. And if you take a limit dl go to 0, you get 3 times mg. The very last reading you're going to get is 3 times the actual weight of the chain. That's just so surprising, you know. That's really surprising. But of course, if you go t equals to t plus dt, then this formula is no longer true. And this is formula 1. F in 1 no longer valid. Now, why isn't valid? Well, what happens? We actually said it was falling, so there were two forces. There's this force and that force. And we had to add those forces. But if you look at t is this thing now, situation is very different. Everything has fallen, everything at rest, and this entire mass is there. That's the situation now. Because this is a new situation, you have a new force diagram. Now, new force diagram is just mg. That just makes it F is going to support, it's just going to require mg. So this is a very important point when you're thinking mechanics. You got to trace in time, and there are moments the force can go jump, okay? It's not like position cannot jump from here to over there. It can't change the value in jump way. And same with the velocity can't, like, you had something going at 2 meters per second and suddenly becomes 10 meters per second. No, that's not allowed, okay? It will have to gradually get there. It can go very fast, but it still has to be continuous, okay? The change can be very rapid but continuous. But there's no such requirement for acceleration, no such requirement for force, okay? So they can jump a situation like here, all right? So you have actually, depending on the time that you will be asked, you have to be careful, you know. Sometimes a question may try to trick you. What happened after this, or infinitesimal after that, things like that. So they're basically testing, when you took a physics course, did you learn to think in terms of infinitesimals or not? Did you think, if you didn't learn how to think in terms of time, then you are going to get tripped. Otherwise, very simple. It's you say, okay, the whole thing just waiting there at rest. What are you asking me? This is just going to be the weight of the chain itself, and nothing like not going to add two more to it. Okay. All right, that's it. So we are done with this problem. If you like this kind of explanations and discussions, and you have subscribed, great. If you haven't subscribed, much appreciate if you subscribe. Yeah. Also, you can spread uh, the information that there's this website. Spread just word of mouth. I really am not asking much. Just tell your friends, and maybe you tell your teachers or something like that. So I will be keep trying to post video more regularly. Interesting problems, some standard problems, some non-standard problems, and so I'll see you in another video. Bye.